Hello, everyone. How is everyone doing? There is no one in my chat. Let me just change to full screen. So, um, last stream I was doing chapter 6, and it was mainly about data types. They showed the presidents. No, not data types. It was more about the operators and the presidents. This time it's going to focus more on bitwise operators. So, this is an optional chapter. It's between 6 and 7. Let's start with the first optional chapter, bit flags and bit manipulation via STD bitset. On modern computer architectures, the smallest addressable unit of memory is a byte. Since all objects need to have a unique memory address, need to have unique memory addresses, this means objects must be at least 1 byte in size. For most variable types, this is fine. However, for Boolean values, this is a bit wasteful. Boolean types have only two states, true and false. This set of states only requires 1 bit to store. However, if a variable must have at least a byte, and a byte is 8 bits, that means a boolean is using 1 bit and leaving the other 7 unused. In the majority of cases, this is fine. We are usually not so hard up for memory that we need to care about 7 wasted bits. However, in some storage intensive cases, it can be useful to pack 8 individual Boolean values in a single byte. Doing these requires that we can manipulate objects at the bit level. Fortunately, C++ gives us tools to do precisely this. Modifying individual bits within an object is called bit manipulation. Bit manipulation is used a lot in certain programming contexts, but not so much in general programming. Graphics, encryption, compression, optimization. Okay. But I want to get into these things later on. So I think it would be quite useful if I learn about bits. Up to this point, we have used variables to hold single values. So 4, 5. Okay. However, instead of viewing objects as holding a single value, we can instead view them as a collection of individual bits. Wait, hold on. In computing, a flag is a value that signals when some condition exists in a program. With a bit flag, a value of true means the condition exists. Analogously, in the United States, many mailboxes have small, usually red physical flags. To define a set of bit flags, we would typically use an unsigned integer of an appropriate size, depending on how many flags we have, or STD bit set. So include bit set, STD bit set of 8. 8 bits in size means room for 8 flags. Bit manipulation is one of the few times when you should unambiguously use unsigned integers, or STD bit set. In this lesson, we will show how to do bit manipulation the easy way via bit set. In the next set of lessons, we will explore how to do it more difficult but versatile way. Given a sequence of bits, we typically number the bits from right to left, starting with 0, not 1. Each number denotes a bit position. So 0, 1, 2, 3, 4, 5, 6, 7. Oh, I see. So they're saying this is the first position, this is the second, and so on. Given the bit sequence, all this, the bits that are in position 0 and 2 have value 1. Manipulating bits via STD bit set. In lesson 5.3, we already showed how to use STD bit set to print values in binary. However, this isn't the only useful thing bitset can do. Bitset provides 4 key member functions that are useful for doing bit manipulation. Wait, I forgot what they did exactly. I want to see how they use the bitset. I can't really remember. So the 4 functions are test, set, reset, and flip. Let's see. Where do they use bitset? Over here. Outputting values in binary is a little harder as stdcout doesn't come with this capability built in. Fortunately, the C++ standard library includes a type called std_bitset that will do this for us. To use bitset, we can define bitset variable and tell bitset how many bits we want to store. Okay. It's bin 1, bin 2. Each of these functions takes the position of the bit we want to operate on as their only argument. Here's an example. So bit set 3 set the position 3 to 1. Now we have 0, 0, 0, 0, 1, 1, 0, 1. Oh, it just flips it from 1 to 0, 0 to 1. Test set allows us to turn a bit on. This will do nothing if the bit is, or this sets the bit to 1. Okay, so there's set and then there's reset. Reset brings the bit to 0. Set brings the bit to 1. Flip toggles the bit. And test allows you to query the bit. Okay, I think member functions would be easier to explain when they introduce objects. Given our bit names can help make our code more readable. So is hungry, is sad, is mad. They're using integers for this. We need 8 bits. Start with bit pattern 0, 0, 0, 0, 0, 1, 0, 1. So me dot set is happy. Me dot flip is laughing. You're using bitset to save space, right? But if you do this, wouldn't that make a lot of int? It's making a lot of integers. Instead of integers, you might have well stored this as booleans. That would have been more space efficient. Unless you're using the define macro. Then it would be quite useful. What if we want to get or set multiple bits at once? Bitset doesn't make this easy. In order to do this, or if you want to use unsigned integer bit flags instead of std bit set, we need to turn to more traditional methods. We'll cover these in the next couple of lessons. The size of bit set. One potential surprise is that bit set is optimized for feed speed, not memory savings. The size of bit set is typically the number of bytes needed to hold the bits, round up to the nearest integer, which is 4 bits on a 32 machine and 8 bits on a 64 machine. Wait. Thus, a bit set 8 will typically use either 4 or 8 bytes of memory, even though it technically only needs 1 byte to store 8 bits. Thus, bit set is more useful when we desire convenience, not memory savings. This will typically use 4 or 8 bytes of memory. But if you do want to memory save, how would you do it with bitset? There are a few other member functions that are often useful. Size returns the number of bits in the bit set. Count returns the number of bits in the bit sets that are set to true. All returns a boolean indicating whether all bits are set to true. Any returns a boolean indicating whether any bits are set to true. None returns a boolean indicating whether no bits are set to true. Size count. Okay. Next one is bitwise operator. Wait, hold on. Okay, no one saw anything. Anyways, 22 pages. Any comments are also included. C++ provides 6-bit manipulation operators, often called bitwise operators. So left shift, right shift, bitwise not, bitwise and, bitwise or, bitwise XOR. Wait. So bitwise left shift and bitwise right shift operators. Bitwise left shifts operator shifts bits to the left. Okay, so 0011. It 1 goes to the right. This one goes to. It goes to the left. They both go to the left. This one goes to the left twice. This over here, the 211 goes to the left 3 times. And then 0 is like uh, the right side receives the value 0. Then bitwise right shift is the opposite side. 1100 bitwise right shift 1. Now you have 0110. Let's run this. So started with the 1100, shift shift this side once, and then shift that side once. So then 1 goes shift once to the right. Now 110 shift once to the left, and you get this. On operators used for input and output, sure programs today typically do not make use of the bitwise left and right shift operators to shift bits. Rather, you tend to see the bitwise left shift operator used with stdcout to output text. Consider the following program. In the above program, how does operator know to shift bits in one case and output X in another case? The answer is that stdcout has overloaded, provided an alternative definition for operator for the insertion operator that does console output rather than bit shifting. The same applies for insertion, no, extraction operator. Yeah, see. Okay. Okay, let's see what they're doing here. Over here it did a bit shift. It like showed the bit value to the console and then an output 1. So that's why the parentheses is needed. Bitwise not. Bitwise not operator is perhaps easiest to understand of all the bitwise operators. It simply flips each bit from a 0 to 1. Okay. So they are doing not of this 0 1 0 0, we get 1 0 1 1. So bitwise OR works like its logical OR counterpart. So 1 or 0 gives 1, 0 1 gives 1, 1 1 gives 1, 0 0 gives 0. Then we have bitwise AND, which works like logical AND. 1 0 gives 0, 0 1 gives 0, 1 1 gives 1. So even in 3 cases, all of them have to be 1. And then XOR, I think it checks whether two are different. So 0 1, these are different bits. 1 0, these are different bits. So it outputs a 1. Over here it outputs 0. 8. It's also possible to violate compound XOR column style. If there are even number of 1 bits in a column, the result is 0. If there are an odd number of 1 bits in a column, the result is 1. So 1 1 1 1 1 1. Okay, so it's about odd or even. If the operands of the bitwise operator are an integral type smaller than an int, those operands will be promoted to int or unsigned int. The result returned will also be an unsigned int, will also be an int or unsigned int. For example, if our operands are unsigned short, they will be promoted to unsigned int. The result of the operation will be returned as an unsigned int. In many cases, this won't matter. However, when using bitwise operator or integral types narrower than int or unsigned int, there are two cases to watch out for. Operator not and operator left shift are width sensitive and may produce different results depending on the width of the operand. Initializing or assigning the result to a variable of smaller integral type is narrowing conversion. Since converting an int or unsigned int to a smaller integral type may result in data loss. This is disallowed in list initialization. Your compiler may or may not complain about narrowing. The following program exhibits these issues. So unsigned int 8. So we have this. Midset 32. Not C. Incorrect. Prints all this. It's incorrect if they did a left shift to 6 values. So wait. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Wait, isn't this correct? Error narrowing conversion from unsigned int to stdu int. Or the compiler won't allow it. Possible warning: narrowing conversion from std int to stdu int. These issues can be addressed by using static cast to convert the result of your bitwise operation back to the narrowing integral type. So the correct, the 1 1 at the end disappears. And this remains 0. So we are only applying not over here. Bitwise operators will promote operands with narrower integral types to int or unsigned int. Operators not and left shift are width sensitive, may produce different results depending on the width of the operand. Summarizing how to evaluate bitwise operation utilizing the column method. Okay. What does 0 1 0 right shift twice evaluate to in binary? I think it would be 0 0 0 1. Yeah. What does the following evaluate to in binary? This or this? So 1 1 1 0. 1 1 1 0. And if they used AND 1 0 0 0. Wait, hold on. Am I reading it wrong? Even though we start here, we read it from the most significant point, right? I think that was my mistake. 0 0 1 1 or this 0 1 0 1 would give this. If you do AND 1 0 0 1, you get 0 0 0 1. A bitwise rotation is like a bitwise shift, except that any bits shift off one end and are added back to the other end. For example, 1101 left shift once will turn into this, but left rotate by 1 would result in 0011 instead. Implement a function that does a left rotate on std bit set 4. For this one, it's okay to use test and set. The following code should execute. I think that's the answer. So we got this binary. So implement a function that does a left rotate. So function, oops, std bit set left rotate std bit set b input. Bin, this is actually b binary input. Now we do left rotate bin, and then we put, does it say once? But a left rotate, implement a function that does a left rotate they haven't introduced for loop yet. Wait. Okay, so I'm assuming they're asking for left rotate once. So left rotate once. Return bin b out std bit set no Boolean takes the entire thing, right? Hold on, I'm thinking how I can do this. So there's an assignment, right? Like this. And then this would do a left shift once, right? Where's the assignment? It's like this. And then I want 1 bit. A storage of just 1 bit. First bit is equal to Wait, before I actually let's just do B. Let's see what I get. Built-in operator cannot be applied to an operand of type std outstream. Built-in operator, it says line 12. Yeah, that was the issue. I did not identify the size. So it says 1101 and now it says 1000. Now let's do test test 1. So this should output either 0 or 1. I'm just checking whether it's 1 from here or here. Or is it 0? So it says 0. Let's see, 2, 3, 0, 4. It's taking a really long time to load. So it says 0. So 0, 1, 2, 3, and then 4 gives an error, right? Did they say what size or did they just say any size? Okay, they said 4 of size 4. Hold on. Let me think how I should do this. I don't think this is efficient. Maybe there's a better way. Test 3. Is null. Let's try this. Okay, I get 1001, which is what I expected. Let's try 01. Let's try this. And then let's try this. Then let's do Y, C, W, Y, Y, C, W. I think I should have done it directly. Okay, now let me run this. It's going to take some time again. How did they implement it? Oh, this is the template they wanted me to follow. Print the following. I keep forgetting I need to do list initialization instead of assigning like this. Okay, pass. Pass again. Pass and pass. Okay, wait. I'm selecting this and I'm pressing the curly bracket, but it's making a new line. How do I prevent that? What's this? Hold on, let me see something. Okay, I need to change that in settings. Redo quiz 2, but don't use test and set functions. Use bitwise operators. Okay, so I can't do test. So Boolean tempt is false, false, and then no, wait. B and one, B and 1 0 0 0. So it's going to make every bit 0, but the last bit will remain the same. And then I can do this and right shift it 3 times. If temp, then boolean b and one one one. No, you or it, right? Or it with these three remain the same. But this definitely, the last bit definitely gets a 1. Now let's see what happens. I don't think I need this temp variable. I can just put this. Oh no, wait, never mind. Syntax error. How do you do or and then assign in one statement? Oh, it's one. It's one of this. Wait, I have an idea. Let me take this. Take this. Oh, they haven't introduced curly brackets yet. So I can't use this either. uh 514 and cannot convert argument 1 from std bit set 4 to boolean. I guess uh, you can do static cast. Yeah, static cast to boolean. Am I doing something wrong? Maybe it's the and. Is it one and? I think it is. Um, cannot convert argument 1 from bit set 4. I keep getting errors. Let's see. bn.cpp 524. So B and 100. No operator found which takes left hand operator of type std bit set 4, or there is no type conversion. I don't understand. Does AND not work with? Hold on. Why is AND not working? Does it only work with 2-bit set? Seeing 1000 as a number. I need to write it like this. And still there is an error. No operator found, which takes a left-hand operand of type std bit set 4. I don't understand what's happening. If I do this, okay, this works. Let's see. Okay, I hope this works. Uh, std cout temp. Okay, this causes an error. Okay, I think this would work. A conditional expression of type bit set 4 is not valid. Like I just want to check one bit. Can I do static cast boolean? It's either 0001 or 1110. So let me see. If case doesn't work, so I need to change this to 0p. Was it the if case the error or line 8? Line 7, 6. A conditional expression of type bit set 4 is not valid. How do you do true or false with this? Okay, I will have to see the answer. Bit 1 does left shift. Bit 3 handles the rotation to the leftmost bit. Bit to 1. This goes here. Oh, I see what they're doing. This shift to one. Uh, yeah, three or bit two. This is what we already want, right? So, for example, if we have 1100, B left shift 1 will give 1000, then B, and then we are ORing this with B right shift 3, so 1 will go at the end. 001. Whoops. You will get this. So this one will go over here, and these three values will go at the front, and then we can OR it. Since this will be a 0, we can OR them to combine the 1 and 0. Okay, let's see. But you can't treat like one bit as boolean. I mean, you have to use the test function, I guess. Let's see. So this gives 1001, this gives 0101, this gives 1011, and this gives 1100. Okay, guess that's a pass. But I looked for help. Bit manipulation with bitwise operators and bit mask. So in order to manipulate individual bits, we need some way to identify the specific bits we want to manipulate. Unfortunately, the bitwise operators don't know how to work with bit positions. Instead, they work with bit mask. A bit mask is a predefined set of bits that is used to select which specific bits will be modified by subsequent operations. Consider a real life case where you want to paint a window frame. If you are not careful, you risk painting only the window frame, but also the glass itself. You might buy some mask tape and apply it to the glass and any other paint you don't want painted. Then, when you paint, the masking paint blocks the paint from reaching anything you don't want painted. In the end, only the non masked paint gets painted. Yeah, I know what they were saying, but I guess the wording is a little confusing. The simplest set of bit masks is to define one bit mask for each bit position. We use zeros to mask out the bits we don't care about and ones to denote the bits we want to modify. Although bit masks can be literals, they're often defined as symbolic constants, so they can be given a meaningful name and easily be reused. Okay, so stdunt mask 0. This is mask 1, mask 2, mask 3. Alright. Because C++11 doesn't support binary literals, we have to use other methods to set the symbolic constant. There are two good methods for doing this. The first is to use hexadecimal literals. So 0 in hexadecimal is 0000 in binary. So we have std int 8. This is hex for this, 1 is hex for this, 2 is hex for this, 4 is hex for this. Yeah, I just want to check one thing. Sometimes leading hexadecimal zeros will be omitted. Instead of 0x01, you will just see 0x1. Either way, this can be a little hard to read if you're not familiar with hexadecimal to binary conversions. The easier method is to use left shift operator to shift a single bit into the proper location. So 1 shift 0, 1 shift 1. Wouldn't this take computation time? Wouldn't it be better to use literals? Testing a bit to see if it's on or off. To determine if a bit is on or off, we use bitwise AND in conjunction with the bit mask for the appropriate bit. So we have this bit over here, 0, we can convert uint to boolean. So flags masks 0. So all of this, because it's an AND case, all of this will become 0. This last case will be 0 or 1 depending on the last case of this. So this function checks the value of this bit 0, and then we are doing the same with bit 1 and so on. So bit 0 is on, bit 1 is off. To set a bit, we use OR in conjunction with bit mask. We use OR equals in conjunction with the bit mask for the appropriate bit. So we want to set the first bit to on. Sorry, we want to set what is this, bit 1 to on. Then we use flag mask 1 or it with mask 1, and it, yeah, this will definitely be 1 then. Resetting a bit if you want to set it to 0. We use bitwise and bitwise not together. We do not with the mask. So for example, not mask 0 will turn this into 1111 1110. Is what I'm guessing. Now what is this example? To reset a bit, we use bitwise and bitwise not. With the okay, flags not mask 2 turn off bit 2. And then they're checking bit 2 again. Some compilers may complain about sign conversion with this line. Why though? stdu8, stdu8, they're the same sign. Because the type mask2 is smaller than int, operator not causes operand mask2 to undergo integral conversion to type int. Then the compiler complains that we are trying to use operator and equal where the left operator is unsigned and the right operator is signed. If this is the case, try the following. Wouldn't it be easier to just work with unsigned integer every time we want to work with these masks? Uh, bit flags. How do you decide when to use bit set and when to use plain integers? Bit set has these useful thing, but uh, I guess doing manipulation natively is difficult with bit set. Okay, to toggle a bit state from 0 to 1 or from 1 to 0, use bitwise XOR. They use XOR here to flip bit 2, then they flip bit 2 again. Bit 2 is on, off, and then on again. So now bitmask and std bitset. Bitset supports full set of bitwise operators, so even though it's easier to use functions to modify individual bits, you can use bitwise operators and bitmask if you want. Why would you want to? The functions only allow you to modify individual bits. The bitwise operators allow you to modify multiple bits at once. So basically, they're making the argument to use the native stuff like integer and bit mask. That would be better than bit set. I guess that's what they're saying. Flags, bit set 8. Mask 1, mask 2. Naming a bit mask 1 or mask 2 tells us what bit is being manipulated, but doesn't give us any indication of what that bit flag is actually being used for. A best practice is to give your bit mask useful names as a way to document the meaning of your bit flag. Here's an example from a game we might write. Is hungry, is sad, is mad, is happy. Wait, what's the storage of int or unsigned int? How many? Wait, no, I'll just check it here. Std cout size of int and size of unsigned. Wait, how do I do unsigned int? Is it like this? Yeah. I need a faster computer. So 4 bytes. Okay, that's actually quite a lot. I went bit 2 down. Okay. Okay. Astute readers may note that the above example don't actually save any memory. 8 separate Boolean values would normally take 8 bytes. But the example above used 9 bytes, 8 bytes to define the bit mask, and 1 byte for the flag variable. Bit flags, uh, 1 byte for the flag variable. Bit flags make the most sense when you have many identical flag variables. For example, in the example above, imagine that instead of having 1 person, me, you had 100. If you used 8 booleans per person, you would use 800 bytes of memory. With bit flags, you would use 8 bytes of bit masks and 100 bytes of bit flag variables for a total of 108 bytes of memory, approximately 8 times less memory. For most programs, the amount of memory saved using bit flags is not worth the added complexity. But in our program, where there are tens of thousands or even millions of similar objects, using bit flags can reduce memory use substantially. It's a useful optimization to have in your toolkit if you need it. There's another case where bit flags and bit masks can make sense. Imagine you had a function that could take any combination of 32 different options. One way to write that option would be to use 32 individual Boolean parameters. Hopefully, you would give your parameters more descriptive names, but the point here is to show you how obnoxiously long the parameter list is. Then, when you wanted to call the function with options 10 and 32 set to true, you would have to do so like this. This is ridiculously difficult. Is that option 9, 10, or 11 that's set to true? And also means you have to remember which argument corresponds to which option. Instead, if you define the function using bit flags like this, then you could use bit flags to pass in options you wanted, option 10 or option 32. This is much more readable. This is one of the reasons OpenGL, a well-regarded 3D graphics library, opted to use bitflag parameter instead of more consecutive Boolean parameters. Here's a sample function call from OpenGL. Clear the color and depth buffer. Okay, GL color buffer bit and GL depth buffer bit are bit mask defined as follows. What is this for? Although bit masks are often used to select a single bit, they can be used to select multiple bits. Let's take a look at a slightly more complicated example where we do this. Color display devices such as TVs and monitors are composed of millions of pixels, each of which can display a dot of color. Each dot of color is the result of combining 3 beams of light, one red, one green, and one blue. The intensity of these lights are varied to produce different colors. Typically, the intensity of R, G, and B for a given pixel is represented by an 8-bit unsigned integer. For example, a red pixel would have R255, G0, and B0. When assigning color values to a pixel, in addition to R, G, and B, a fourth value called A is often used. A stands for alpha and it controls how transparent the color is. If A is 0, the color is fully transparent. RGB and A are normally stored as a single 32-bit integer with 8 bits used for each component. Following program asks the user to enter a 32-bit hexadecimal value and then extract 8-bit color values for RGB and A. Oh, so red bits, green bits, blue bits, and alpha bits. Why do they need to mention 32? Can't they just do unsigned int? I guess it would be unsigned int might be different and different architecture. So you went 8. Okay. Given the following program, add a line of code to set the article as viewed. My article flags, option favored, option viewed, edited, favorited, shared, deleted. Wait, if this is taking a lot of memory, no, I think this is fine. Uh, can't we use the define macros instead of using like 8 bits of our memory? So std and my article flags options favorited. Add a line of code to set the article as viewed. So they tell us not to use bit set. Okay. So what they want is std. No, wait. My article flags is now my article flags option favorited or we don't need a new line. We can just add or option viewed. But it says add a new line. So we can just do this option viewed. Now let's see. The not operator changes the bits to 32, right? So 1 and 2, 4. Okay. Add a line of code to check if the article was deleted. If my article flags, you and it with option deleted. There is no curly bracket yet. STD out article deleted. Option deleted. Right. And then if we actually, it's easier if I do this. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So you have favorite. This isn't easier actually. Let's say I have the favorite on and the option deleted on. Oh, now it says article deleted. And then add a line of code to clear the article as a favorite. Okay, and then clear it as a favorite. My article flags is now not favorite anymore. Is now how do I do not, like the not operator, without converting it to integer? So static cast std uint 8 underscore t. Is this correct? So we have not options favorited. So everything becomes 0 uh, except the third bit. But over here it's flipped. And we are doing AND with that. Conversion from int to uint. I don't know what they're saying. Oh, this worked. So article delete. And the favorite flag is not set. Why are the following two lines identical? I forgot what the De Morgan's law, I think. Yeah, De Morgan's law. You can check the truth table to prove that statement. In the following examples, we assume that we are dealing with unsigned integers. Consider the 8-bit binary number 01011110. This binary means 0 times 128 plus 1 times 64 plus 0 times 32. We sum up all of these parts, we get a decimal number 94. Here is the same process in table format. We multiply each binary digit by its digit value. Right. So converting binary to decimal. So method 1 for converting decimal to binary. Converting from decimal to binary is a little more tricky but still pretty straightforward. There are quite a few methods to do this. In the first method, you'll continually divide by 2 and write down the remainders. The binary number is constructed at the end from the remainders from the bottom up, converting 148 from decimal to binary. Using R to denote a remainder. So 148 divided by 2 is 74. 74 divided by 2 is 37. 18 and the remainder is 1. 9. 4 remainder is 1. And then the remainders make up the binary. So 1 0 0 1 0 1 0 0. Method 2 for converting decimal to binary. In the remaining two method, we will work forward calculating each bit as we go so that we don't have to reconstruct the binary format at the end. Consider the decimal number 148 again. The largest power of 2 that's smaller than 148 is 128. So we will start here. So 148 is greater than or equal to 128. Yes, so the 128 bit must be 1. 148 minus 128 is 20, which means we need to find the bit worth 20 or more. Is 20 more or equal to 64? No. 20 more or equal to 32? No. Is 20 more or equal to 16? Yes. So the 16 bit must be 1. 20 minus 16 is 4. Is 4 greater than or equal to 8? No. Is 4 greater than or equal to 4? Yes. So the 4 bit must be 1. Then we are left with 100, 10100. So method 3. This method is a variant of method 2 that uses integer division. Consider the decimal number 148 yet again. The largest power of 2 that's smaller than 148 is 128. So we would start there. 148 divided by 1 with some remainder. Since 1 is odd, this bit is a 1. 148 divided by 64 is 2 with some remainder. Since 2 is even, this bit is a 0. Oh, they're checking the even and odd quotients. This method isn't great for humans as it requires a lot of division. It's also less efficient for machines since division is an ineffective operation. Let's convert 117 to binary using method 1. So you check the remainders and the answer is 1110101. Method 2, you check with each power of 2. Then adding in binary, in some cases you will just see one in you will see one in just a moment. It's useful to be able to add two binary numbers. Adding binary numbers is surprisingly easy, although it may seem odd at first because you're not used to it. Consider two small binary numbers. Let's add these first, line them up as we have before. Then starting from right and working from left, we add each column of digits. So it's like 0 plus 1 is 1, 1 plus 1 is 2, but in binary that's 1 0. So put tiny, wait, hold up. Let me just get my tablet. It would be like how you do division and with decimals. It's the same method. So they have 0 1 1 0 0 1 1 1. This is from last stream. 0 1 1 0 0 1 1 1. We add them, you get 0 plus 1 is 1, 1 plus 1. So 1 plus 1 is 2, just like this. So we write carry 1 here, then 1 plus 1 plus 1, which is 3. So if we do plus 1, this is 3, and then 1 over here. It's like how we do division in decimal. Signed numbers and 2 complement. In the above example, we have dealt solely with unsigned integers. In this section, we will take a look at how signed integers, which can be negative, are dealt with. Signed integers are typically stored using a method known as 2 complement. In 2's complement, the leftmost bit is used as a signed bit. A 0 signed bit means the number is positive, and a 1 signed bit means the number is negative. Positive signed numbers are represented in binary just like positive unsigned numbers. Negative signed numbers are represented in binary as the bitwise inverse of the positive number plus 1. Here's how we represent -5 in binary 2's complement. First, we figure out binary representation for 5, which is 1, 2, 3, 4. So 1 plus 4. So 2's complement would be, 1's complement would just be inverting. And then you add 1, right? Yeah. And 2's complement would just add 1. This would be -5. Converting binary to 2's complement to decimal. To convert this from 2's complement into a decimal number, given this, invert the bits, add 1, convert to decimal. Since the original sign was negative, the final value is minus 98. Shouldn't we subtract 1 first and then invert the bits? And this convert to decimal. There's another method that's easy to calculate by hand. In this method, the sign bit represents a negative value. All the other bits represent positive values. Sign bit is minus 128. All the other ones are positive. And then the result is minus 98. Why types matter? Consider the binary value 10110100. What value does this represent? You probably say 180, and if this were an unsigned binary number, you would be right. However, if this value was stored using 2's complement, it would be minus 76. And if the value were encoded in some other way, it could be something else entirely. So how does C++ know whether to print a variable containing binary or as 180 or minus 76? In case the section title didn't give it away, this is where types come into play. The type of the variable determines how a variable's value is encoded into binary and decoded back into the a value. So if the variable type was an unsigned int, it would know that 10110100 was a standard binary and should be printed as 180. What about converting floating point numbers from to binary? Okay, they don't go through the tutorial. Convert this to decimal. Okay, I guess I will end the stream here. And then next stream, which may happen later today, I'll try to finish chapter 7. Okay. Okay then. Guess see you guys next time.